control or a good handle on making Lewis structures, we're going to take it a step farther and looking at some of the bonding that occurs with structures. When you have several structures possible of the same molecule, and the trick to this is you must have the same atomic arrangements and the attach points. If you can make structures, Lewis structures that are accurate, follow the rules, and they're equal. So here you were going to call this oxygen A, B, and C, A, B, and C. So in this first structure, we have the double bond between A and B. In the second structure, we have it between B and C. So these structures are equal in terms of their Lewis structures. And we say that they are resonance structures. And we designate a resonance structure, but not a double arrow. Remember, we talked about that when we talked about weak electrolytes. That's a totally different thing. That's equilibrium. This double-headed arrow means that these are comparable structures. And they only differ by the arrangement of the double bond. So the best description of the true structure when you have multiple options is a resonance hybrid. So a resonance hybrid structure is a mixture of all the possible structures. So for example, if we have 2 to 1 and 1 to 2, then your best option is 1.5 for each bond. So up here they've got the description of blue and yellow makes green. So you take some blue paint and some yellow paint, and they're equal paints, but you mix them together and you get the green paint, which is the true structure if you mix these hybrids. So if you look at it, basically the resonance structures differ in the location of the double bond. So this actually will also apply to triple bonds. So what we're looking at is single bonds cannot move, but you can move double and triple bonds around. So in this case, the double bond is here, then it's here, then it's here. So it's going to keep rotating around. So in this particular case, we have 3 different options available. Because the electrons are moving, we're going to say if I could spell delocalized. We say the electrons are delocalized. Remember, we saw that a little bit ago when we talked about metallic bonds. And remember, the rule to delocalized electrons is the electrons are in motion. They are not associated with a particular atom. They can keep moving around. Now, resonance structures differ from isomers, which have the same chemical formula, but different atomic arrangements. So you actually move the arrangement. So this is not a molecule, but if you have A, B, C, where B is the central atom, okay, then a resonance effect for this one is as if you have a double bond and it's A double bond B, C. That's a resonance. But if you have A, C, B, that's an isomer. And in no way, shape, or form are these equivalent. Okay, they're not equal. Because the atomic arrangements are different. So if you have different atomic arrangements, you do not have a resonance structure. So here we go. We've got some problems here. And for simplicity's sake, because I know I'm going to move things, we're going to start with the numbering. So 6 plus 6 times 2 is 18. So here we're going to have sulfurs are central. Whoops. So we're going to have oxygen on either side. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So in this particular case, and I'm going to color code it, we could take a pair from this oxygen, and so we get oxygen double bond sulfur, oxygen. And remember, when you write the full structure, you've got to include all the other electrons. And if we took it from here, we would have this oxygen as a single, the other one as a double. And because it's resonance structures, we would put our double head arrow in here like this. So these are equal. It's just a difference in position of the double bond involved between the sulfur and the oxygen. Now, one thing I do want to point out about this molecule, if you look at it, sulfur can exceed the octet. So you could double bond each sulfur to oxygen. Don't do that. That actually is what comes up in a lot of models if you're using online, but that really doesn't exist because it has all kinds of energy considerations and rearrangement of orbitals, etc., that are above your pay grade, so just go with the simplest one you've got. All right, so let's go up here, and we're going to have 6 plus 4 plus 5 plus 1, which is 16. So I'm going to set it up as sulfur. In this case, sulfur, carbon is the central atom. How do you know that? I just told you. Otherwise, I'd have to tell you like carbon is central. Else you would go with sulfur. So we have nitrogen here. So we have 2, 4, 6, 8, 10, 12, 14, 16. So remember, we have to fill the outermost electron shells before we can do the interior. That being the case, carbon's not happy. So we have 3 different options here. The first option is we can take 2 pair from sulfur. So I'm going to write that one here. So that's sulfur, triple bond, carbon, nitrogen, the lone pair here. Now, this is an ion, so it does get the brackets. And the other option that somebody may have seen is, well, forget sulfur, let's take both of them from nitrogen. So if we write that one, and I'm going to do this one off to the side, sulfur, carbon, triple bond, nitrogen. So sulfur has its octet with lone pairs. And again, it is an ion, so we're going to put it in brackets. And then somebody else is like, wait, I could take 1 pair from sulfur and 1 pair from oxygen. Sure enough, you can. So you end up with sulfur, carbon, nitrogen, and each of these have 2 other lone pairs. Again, goes in brackets. Now, because these are resonance structures, I'm going to draw the arrows in between all of them. Do I have any more? No. How many structures do you have? As many as you need. So, this comes into play for a variety of things. Now, this next compound, I don't want you worrying about counting electrons. I'm going to go ahead and show you. We have CH3 that takes care of 1 carbon and 3 hydrogens. So then we have a carbon and 2 oxygens. So when you set this up, you'll end up with either this structure, has a negative on it here, or this one can resonate into CH3, CO, negative here, double bond here. This is what you're going to do in organic, and I'm going to show you what's actually going on. What happens is this pair comes in here, and this pair goes up here. Notice that I'm moving 2 electrons at a time. That's a double-headed arrow. If I was moving 1, it'd be a fishhook. So in organic, we would do this. Again, And so one option is to move this double bond to here, in which case this positive would end up here. And then you would end up with this structure here, which could then migrate over here, in which case the positive moves as you go. You really shouldn't show the positive moving. I was just showing you position. So then that would give you the third position, which is this one right here. And these are resonance structures. Now, these are organic resonance structures. They are important, don't get me wrong. However, we're in inorganic chemistry. I want you to really focus on the top two. The bottom two, I just wanted to show you what you would see in the future. All right, so we talked about the concept of, wait, how do we tell who's got the best? Who's got the electrons? How do you know which one is the best? Well, the trick to determining what the best structure is in resonance, or in general, whether a structure is kind of possible, is to look at the formal charge. Now, the formal charge is basically a bookkeeping methodology to count how many electrons each atom has, if they're sharing them. You're not making ions. There you can see it obviously. Here you're just trying to figure it out. So what formal charge is you start with the valence electrons, which is Va. Then you're going to find the non-bonding electrons. And so sometimes you'll see V minus non-bonding. And then you're going to get half of the bonding electrons. So I tend to use this formula on the grounds that NB works better for me than NA, but that's okay. So the rule of thumb is the sum of the formal charges has to equal whatever the charge is on the component you're looking at. If it is a neutral molecule, then it must equal 0. If it's an ion, it has to equal the charge. So let's look at some formal charges. Oh, one other thing. When you have a variety of structures to look at, and you're trying to determine the best structure, then you want to know what is a good structure. Well, first off, you want the smallest formal charge favorable. You want the negative on the most electronegative species. So basically, if you have the choice between carbon and oxygen, you want the negative to come out on the oxygen. You don't want a negative on a carbon. You don't want like charges, so if you had that, which that's not real, but if you had a plus and a plus, that's bad. You want opposite charges, so I reversed it. I hate it when I do that. So on this one, if this one is a positive, this one's a negative, and that one's a positive, then that's favorable. Again, these structures are not real, just showing you example. Okay? So let's actually look at real structures and look at it. And we're asked to calculate the formal charges in the following. So what we're going to do is, first off, we have to draw the structure. So that's 1 plus 6 plus 7 is 14. So this HOBr. The O would have to be the central. So we have 2, 4, 6, 8, 10, 12, 14. Everybody's happy. So we're asked to do the bromine. So the formal charge for bromine is 7 valence electrons, minus any non-bonding, which we count these as our non-bonding. minus 6 minus, these are the bonding, half of the bonding, which is 2. So 7 minus 6 minus 1 is 0. So the formal charge here in HOBR is 0. So over here we have B, F, 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 and F. So that's 3 plus 28 plus 1. It's 32. So that would put this in here. Now notice on the previous compound, it was neutral, so the formal charge of all the species should come out to be neutral. This one, on the other hand, is minus 1. So somebody's going to come out to be minus 1. We want the boron. So we want the formal charge of boron. So that's 3 minus 0, because there are no non-bonding electrons, minus 1/2 of all the bonding electrons, which is 8. So that's 1 minus or 1 or minus 1. So that's the atom that holds the formal charge. Okay, so here are 3 resonance structures, and we could make sure that we see them as resonance structures here by drawing this arrow. And the question is that which structure represents the best bonding? So the first thing we're going to do is calculate the formal charges. So I'm going to designate this N1 and this N2. So the formal charge of N1 is going to be equal to 5 minus 2 valence non-bonding electrons minus half of the 6 bonded electrons. So that one's got a charge of 0. The second nitrogen has, again, 5 valence electrons, has 0 non-bonding electrons, and has half of 8 electrons, so it's 1 plus. The formal charge of the oxygen is equal to 6 minus 1/2 of 2, which is minus 1. So here we have formal charges of 0, plus 1, and minus 1. So remember, they should total to equal what they have, which is 0. So let's go on and do structure number 2. And I'm going to go ahead and stack it. Again, this is 1 and this is 2. So formal charge of nitrogen 1 is equal to 5 minus 4 non-bonding minus 1/2 of 4. So 5 minus 4 is 1, minus 2 is 1 minus. Formal charge of N2 is equal to 5 minus 0 minus half of 8, which is 1 plus. Formal charge of oxygen is 6 minus 4 minus half of 4, which is 0. So the total charge here equals to 0 on your formal charges. If your formal charges do not equal what the charges your species is, that is a good sign immediately that some of your math is wrong. Okay, so I'm going to switch colors again. Again, I'm going to call this nitrogen 1 and nitrogen 2. So here a formal charge of N1 is equal to 5 minus 6 minus 1/2 of 2, which is 5 minus 6 is minus 1, minus another 1, that's 2 minus. Formal charge of N2 is equal to 5 minus 0 minus 1/2 of 8, which is 1 plus. And the formal charge of oxygen, 6 minus 2 minus 1/2 times 6, which is 1 plus. Yep, equals 0. Okay, now a couple things to look at. Notice that the central nitrogen never changed in terms of it only had 4 bonds and no lone pairs. So the formal charge for it never changes. So that's one thing to note. So then that asks the question is what represents the best bonding? Well, sometimes the easiest thing to do is throw out something. Is there one you can throw out? Oh yeah. This structure can go because it has high formal charges. Every other formal charge is 0, plus 1, or minus 1. This one actually has 2 minus, so we want to chunk it. And, added bonus, it has 2 positives sitting next to each other. So there you go. We're done with this one. This is the worst structure. So we're left with structure 1 and structure 2. Remember we discussed that in both cases, the nitrogen is in the center, then the N2 stays the same. So that's no help. So we have to look at the other sources. So on this structure 1, oxygen is negative. On structure 2, nitrogen is negative. Well, remember the rule. We want the lowest formal charges, which both structure 1 and structure 2 qualify as. And then the other thing is we want the negative on the most electronegative species. So, who is more electronegative? Oxygen or nitrogen? Oxygen, because the negative is on the oxygen here. So, not only does it have the lower formal charges, but it has them in the best locations. So we're good on that. So if you're given resonance structures, you may also be asked to calculate the best structure possible. So that brings us back to these structures. So we're going to, well, normally I would go back because you're taking notes, but I'm going to real quick draw them in. So this one really didn't matter because it was S double bond O, O double bond there, or S double bond O, O. This one was the problem child, and it's S triple bond carbon, single bond nitrogen, lone pair here, lone pair here, lone pair. The second one was sulfur, lone pair, double bond carbon, double bond nitrogen, pair, negative. Oh, I forgot to put the negative on that one. Third structure was sulfur, single bond, 3 lone pairs, carbon, triple bond nitrogen, pair, whole thing is negative. Okay, so let's go back and look here. So if the oxygen has the double bond, and I did not put in the lone pairs here, nor did I put them here, but they're the same in both ones. The oxygen with the double bond is going to be 6 minus 4 minus 1/2 of 4, which is 0. With the single bond is 6 minus 6 minus 1/2 of 2, which is 1 minus. The formal charge of sulfur is 6 minus 2 minus 1/2 of 6, which is 1 plus. So in this particular case, you're either going to put the negative on an oxygen or you're going to put the negative on an oxygen. So in this case, neither is favored. Okay, we're not going to worry about these at all for this type of problem. So we're going to do our math here. So the formal charge of sulfur is going to be 6 minus 2 minus 1/2 of 6, which is 3, so that's going to be 1 plus. Formal charge of carbon is going to be 4 minus 0 minus 1/2 of 8, which is 0. Formal charge of nitrogen is going to be 5 minus, oops, I just realized I didn't do that one right, minus 6 minus 1/2 of 1, which is 2 minus. The blue one is formal charge of sulfur is 6 minus 4 minus 1/2 of 4, which is 2, 0. Formal charge of carbon is 4 minus 0 minus 1/2 of 8, which is 0. Formal charge of nitrogen in this structure is 5 minus 4 minus 1/2 of 4, which is 2 minus. That doesn't make any sense. 5 minus 4. Okay, that one's 2 minus. Let me go back and check my sulfur, because what I'm realizing is 2 plus 0, 0 is 2 minus, so that's not going to fly. So let me check. We have 6 minus 4. Well, we shouldn't do that. Which is 6 minus, let me erase it because I can't read it. Which is 6 minus 4 minus 1/2 of 4, which is 2. Well, that would be 0. So 5 minus 4 minus 2 is 1 minus. I just can't do math. All right, checking my math there. All right, the last one then is formal charge of, let me back that up because I'm going to run out of my corner here. Formal charge of, that doesn't look right, sulfur is 6 minus 6 minus 1/2 of 2, which is 1 minus. Formal charge of carbon, and if you don't want to do this one again, we've done it 4 times, so it's still 0 3 times. So the formal charge of nitrogen is 5 minus 2 minus 1/2 of 6, which is 0. All right. So then it says determine the best structure. Well, if we're looking at it, which one are we going to eliminate? The first one. This one is going to be eliminated because it has high formal charges. We don't like it. So that leaves us with this one for consideration and this one for consideration. Now in this structure, the negative is on the nitrogen. Here, this one, the negative is on the sulfur. So this is going to be your best one because nitrogen is more electronegative than the sulfur. So what we did was we set up our structures, we did the formal charges, and even though we have 3 options available, and the true structure lies somewhere in between, it may actually be favored by one because of the formal charges. So in this particular case, this is my best structure with the 2 double bonds because it puts the negative on the nitrogen and not on the positive. Okay? So this allows us to do resonance structures and identify whether they're good or bad. You want to keep this in mind as you're working the problems, and you do want to determine which structure is best when you're doing resonance, and you may want to work on extra problems of these because these take a little bit of time. So it helps tremendously if you have it correct. All right, so we're done with this section.